Good morning, good afternoon, good evening to all of you, and welcome to this second edition, second talk for the Thermal Transport Café. Today we have Matevz Zupancic from University of Ljubljana, who is gonna give us a talk in boiling phase change. Before I start with more detailed introductions, I would like to remind you all that this meeting is being recorded and videos will be distributed soon. In last session, a few weeks ago, we had 𝗂𝗍𝗿𝗀𝗁 from University of St. Louis. And if you would like to get the video, please contact the following email information here. I would like to remind you to please be respectful and constructive with all your comments. Let us try to, during the talk only, let us try to keep our cameras on and microphones off, cameras and microphones off so that there is better bandwidth. I would like to give another announcement. So we have the first mentoring session this January, led by Professor Srinivas Karimella, with an exciting title, Navigating the Tenure Journey. And the date and time will be disclosed on a later note. And I was told that this presentation actually conflicts with the UFC workshop that starts in 1 hour. So you are more than welcome to leave the talk as soon as you need so that you can accomplish also joining the other talk. Because of the time constraints, I will just be very briefly. For those of you that don't know me, my name is 𝗂𝗍𝗁𝗀𝗀. I'm a lecturer in chemical engineering for the Institute of Multi-Scale Thermofluids at the University of Edinburgh. And today I have the privilege to introduce my research colleague and friend, Matevz Zupancic. Matevz is an assistant professor at the Faculty of Mechanical Engineering of the University of Ljubljana, with interest on heat and mass transfer, more specifically in phase change and boiling. I don't want to spend time on repeating the information that you all have on the flyer. So just to say that I met Matevz in 2017 when he was about to finish his PhD. We met at the 𝗂𝗍𝗁𝗀𝗁 conference. At that time, he had a baby that he must be around 4 years old now. And since then, we have shared some other conferences. We have also joined the panel for the 𝗂𝗍𝗁 for as young career scientists, advising young researchers and young postgraduate students. We have also met at the International Conference of Boiling and Condensation in Nagasaki, always with very nice discussions, very nice moments, and sharing also wines, drinks, and karaoke. So this is all from my side, Matevz. I think you have around 20 to 25 minutes for your presentation. I will activate my camera once 20 minutes is passed, so to kind of give you a signal that you have around 5 minutes left. So the floor is yours.
Thank you, Danny, for this beautiful presentation, introduction. Do you hear me loud and clear? Do you see my screen?
All good, all perfect.
Yeah, okay. So as Danny said, my name is Matevz Zupancic from Ljubljana, and I would like to thank you, MD, and Mateo, of course, and all the entire community to give me a pleasure of discussing you this topic today. I was encouraged by Mateo to give a brief introduction to our lab work as well and my, let's say, career. So I started in 2008 in the bachelor's program in the same faculty that I'm still today. And I continued in 2011 in a master's program with the lasers and mechatronics. So I only started with pool boiling and boiling heat transfer in 2013, as I started a PhD under the leadership of Professor 𝗂𝗂𝗁𝗂𝗁𝗂. And today I'm assistant professor, and I just got founded my first project this year. And most of the work discussed today will be related to the project we are starting. It's worth of 3 full-time equivalents. It will last for 3 years. So I will not give you a lot of answers today. I will rather give you a lot of questions that I have, maybe even for you. So about the research we do in our lab, we mostly do boiling heat transfer. This is my topic. We also discuss and develop the enhanced measurement techniques, mostly temperature measurement techniques based on the fluorescence. We do also flow boiling, and last but not least, we are involved in Ruby experiment, ongoing research experiment on boiling heat transfer in microgravity. With the industry, we do a lot of work mainly to get, basically to get money for the research. We do a lot of industrial measurements, temperature, infrared, high-speed measurements in different environments. We do simulations of boiling chambers, for example, and my passion in industrial field of research is development of filtration units. This is one of our latest, let's say, products. So today we will be discussing pool boiling heat transfer. And I will just point out the most common research questions in pool boiling heat transfer. So let's define ourselves a process, and let's define the fluid. And let's say we have water. We could have anything else between water and FC72 if we want, like in terms of the surface tension, right? And the most common question is, what will the boiling curve look like in this on this surface? What will be the CHF? What will be the onset of boiling? And the second most common question is, how can we enhance this process? What can we do with the surface or with the environment itself to enhance boiling heat transfer? But we rather took a different path, especially with our project. We stick with the boiling heat transfer, and we even give ourselves the boiling curve. And the question we ask ourselves is, how will this boiling curve look like within a year, within an hour, within a half an hour, within 100 hours of operation, whatever you want? And to answer this question, we need first to define a starting point. So we somehow used what we thought is the safest starting point you can find. So taking copper surface, pool boiling of water under 1 atmosphere, thick sample, there is no thin foil or anything, and just did a literature review, like what is the CHF on this untreated copper surface? And this is the result. I mean, what do we know really about the boiling? I mean, this is 35 kelvins of difference and 1 megawatt across in y-axis. And this is the window of experimental results. And we thought like we knew everything, but we realized we know nothing. We are looking now at this at the phenomena that should be the same. I mean, everything should fall, let's say, within this circle. And we could even say, okay, everything what doesn't fall within this circle was wrong, was measured wrong. But I don't agree with that. Simply, I don't agree with that. We evaluated what is with the roughness of the surface that Autor published. What is with the heater design, either is monoblock or separated surface. What is with calculation methodology and general uncertainty. And we found even with all the contributions, we cannot explain the scatter that we observe here in current literature. And this is because the surfaces simply with boiling simply have some sort of a memory effect. If we go back almost 100 years ago with the research of Jakob and Rinke, they found that HTC will decrease over time due to the reduction of nucleation's high density, mostly because the less and less air is trapped in the cavities. And 20 years later, 𝗧cie Molotz, and she found that reaching a stable boiling performance requires at least 100 hours of operation. And this is again connected with the gas entrapped in the cavities. So if we think of our research, none of us probably, I mean, not a lot of us did 500 hours of operation before we measured our first boiling curve, right, on the let's say, a reference surface. But all of this on the left side is somehow related to the gas. But recent results, let's say from 2019, researchers found that copper surfaces, in this case, they use graphene oxide copper-coated surfaces, underwent some sort of a natural hydrophobization process. So under boiling circumstances, the surfaces become hydrophobic. And this significantly changed boiling performance, or can it change? In our case, we used copper surface which was sanded or laser textured, and we found similar results, but we got to that results really fast. So we, let's say, measured few boiling curves, which were very stable, either with laser textured or untreated surface. These are blue lines. And then we reached CHF at one point, and after reaching that, the surface enhanced in HTC, heat transfer coefficient. The CHF went down a little bit, but what caused that change? Actually, all the surfaces were de-oxidized. So from the cupric oxide, we got cuprous oxide and the Cu metal. So the oxygen content in the surface went down in all cases. So we can see that by the XPS analysis. And these have two consequences. So change in surface chemistry actually also changes the surface morphology. So we found some sort of truncated octahedra on the surface that weren't there before. So submicron surface morphology changed in the nanoscale. So, and secondly, the wettability changed. So all the surfaces went towards hydrophobic state. So I'm trying to show you that surfaces that we measure have some sort of a memory effect, and we must know exactly what we did with surfaces, how we prepared them, and how we treated them prior to making boiling experiment. And this natural hydrophobization during the boiling doesn't only takes place during boiling. It can also happen on air. For those who don't know our research, we do a lot of our boiling experiments on laser textured surfaces. So at the moment, we can produce many different kinds of textures, and we already know that laser texturing completely changes the crystalline structure of the surface, as seen on the EBSD analysis here on the top right. But the most important conclusion here is that surfaces after laser texturing are mostly superhydrophilic. So they are completely wetted in a saturated �ędzel regime. And this is mainly due to the oxidation of such surfaces. We can see that oxide content on such surfaces is by weight reaching 30%, which is a lot. And these oxides are intrinsically hydrophilic, which given the microstructure of the surface causes the superhydrophilic state. But after time, this is what happens, and this is a usual behavior. So we can see after 10 days, 80 days, 100 days, a superhydrophobic state. And there are multiple explanations in the literature why this happens. And we mostly believe this is due to the absorption of hydrophobic contaminants that are naturally present in air. And we saw that sort of naturally occurring hydrophobization on surfaces after they have been treated with laser with completely different parameters. So the final state after 1 year is highly hydrophobic or superhydrophobic state. And now the question is, okay, is this superhydrophobicity even stable in boiling operation? And short answer is no. So this is an example of superhydrophobic stainless steel surface prior boiling, and after first boiling experiment, the superhydrophobicity goes away. And if we see that on a boiling curve, this is the first experimental run. We can observe very low onset of nucleate boiling, early transition to nucleate boiling, and in the second run on hydrophobic surface where the hydrophobicity was gone, this low onset of boiling is also gone, right? And we can kill this superhydrophobicity in two ways. One way is to boil on the surface, and the second way is to prepare superhydrophobic surface in contaminated furnace, and then give this surface to non-contaminated furnace at 350 degrees, and these hydrophobic contaminants simply burn away. But general conclusion here could be, okay, we actually don't have to concern so much about this naturally occurring hydrophobicity on the surfaces after being treated with laser. Well, that's not really a general conclusion, because we just recently found that, for example, on copper, this naturally occurring hydrophobicity is very stable. So we have before and after boiling experiments and found that this super, or let's say highly hydrophobic state cannot be simply flushed away after boiling or even after reaching a CHF. Just to provide you a few detailed information about boiling on such surfaces and this washing away the superhydrophilic properties. When you perform boiling experiments on superhydrophobic surface, initially you get very small bubble footprint diameters. And in the second run, these bubble footprint diameters are much bigger, in the range of 1 millimeter. And this is the case for boiling on thin metal foil, for example. So there is a difference in footprint. There is complete difference in bubble dynamics, and I will leave that to discuss later a little bit. I would just like to take you back around 2 or 3 years, and firstly explain why do we even bother with boiling on hydrophobic or superhydrophobic surfaces. Initially, what was thought is that superhydrophobic surfaces with water are completely useless, because this is the usual boiling behavior we could observe after submerging the surface, starting the boiling experiment, degassing even the fluid completely. And we find that the transition to film boiling happens at very low heat flux. And this is the result we published in our paper. And it actually goes along with the criteria published by Коваль, who said that the nucleation temperature on the non-wetting surface, so ideal non-wetting surface with a contact angle of 180 degrees, should be 0. So the nucleation temperature superheat should be 0. But this was theoretical study based on the smooth surfaces. In our case, we cannot produce smooth superhydrophobic surface, right? We also will always have a microstructure in below. And there is another, let's say, study by Fritz and Funk, who defined bubble departure diameter in relation with the static contact angle, and we can see their approximations are completely different. So what is actually going on? I mean, can we really effectively boil from superhydrophobic surface? And 2 years ago, 𝗂𝗂𝗁 said, yeah, we can. So they found that vapor trapped in the surface can be effectively removed, and we can initialize boiling not from the 𝗂𝗰𝗵𝗁𝗁 state, but rather from Wenzel state. And if we initialize boiling from the Wenzel state, we can get boiling enhancement even on superhydrophobic surfaces. So in this case, the term superhydrophobic can be or may be used with caution. So is the surface really superhydrophobic if you completely fill it with water, or is there some other term that should be rather used or explained? And okay, they found that they can easily reach Zuber prediction even on superhydrophobic surfaces. And in some other case, when the boiling is initiated from the 𝗂𝗰𝗵𝗁𝗁 state, they get this early transition to film boiling, so useless from the application point of view. And it got us thinking. So we wanted to develop the same surface that would have the same properties. And what we did, we took the laser textured surface, which is filled with microcavities, so a lot of nucleation sites. We borrowed the CVD treatment from Nenad Milković lab, and we CVD treated the surface with the HTMS coating, so it's a silan coating, which produced some sort of a stable hydrophobic surface that can survive boiling. And we found that after laser texturing, the reference surface got enhanced with regarding the CHF value and the HTC. So this is the transition after laser texturing, and after hydrophobization, which made the surfaces super hydrophobic, it enhanced boiling performance even further, up to 200 kilowatts per square meter Kelvin was the highest recorded heat transfer coefficient in our case. And this is an example. How can you initiate boiling from Ksey-Baxter or Wenzel regime? So this is the reference surface, and if you don't degas properly, this is what you get. And if you degas properly, this is what you get. But all of this happened on the same surface, and all of the surfaces, or this super hydrophobic surface, really had stable super hydrophobic properties. So the surface exhibited super hydrophobicity before and after experiment, if we put a drop of water on completely dry surface. So there is still a big question, and this is a question I cannot explain, is why, even when the surface is super hydrophobic, why there isn't a vapor covering the entire surface immediately after the nucleation? I mean, it makes it obvious that if a vapor, an air is trapped, you get immediate coverage of the with the film. If it's filled with liquid, and even after this small vapor forms in the surface, in the cavities, the vapor simply doesn't cover the entire surface. So a force, in this case, some force is attaching the liquid strongly to the surface. And to see a little bit what's going on let's say on micro scale, we did some experiments together with Mao Takayama and Professor Kunugi. We did experiments in Ljubljana with the micro thermocouple. So we used our setup with infrared camera and put a micro thermocouple above 3 by 3 nucleation sites. So we can see those nucleation sites on an infrared image here. And in one case, we developed laser textured cavities that were super hydrophobic, non-degassed. In the other case, super hydrophobic and degassed. And we could see that if we first focus on high-speed infrared measurement, this is the blue curve on the left side, when the surface is non-degassed, there is hardly any significant temperature fluctuation. And if we calculate the energy removed by a single bubble, we can see that the energy is in terms of 0.1, 0.2 millijoules. While on the right side, if we check on the blue curve, we see this commonly seen boiling activity and temperature fluctuation underneath a growing bubble, and the energy removed by a single bubble here is in terms of 1 millijoule, 1.5 millijoule, or something like this. So this is a completely different boiling behavior. And if we now see the red lines, and this is a temperature measurement from the micro thermocouple that is put 100 microns above the surface, we can see that in the left case, where the surface is non-degassed, the thermocouple measurement is around 100 degrees C all the time. So this basically means that it's in the vapor phase all the time. The bubbles that detach from the surface immediately form another bubble and immediately form another bubble and so on. While on the right side, it's a completely different story. And these are the only 2 videos that I have for today. I will try to start them. It will not be synchronous, but still you can get the feeling. So the left side is non-degassed boiling activity. The right side is degassed. And I mean, why am I even explaining this? We should say, yeah, when you do a research, you should always take care you degas the surface. That's right. But is it really possible to do it in the application when you expose your surface to some real life experiment? I mean, what would you observe? And most importantly, what will you observe after 500 hours or 1,000 hours of operation? Will the surface naturally degas once? Or is the gas or air, whatever is trapped, so stable in these vapor trapping cavities that it will stay the same for a very long time, right? So now, at the moment, we developed many different surfaces that can produce you the same boiling performance. So I'm speaking about enhanced boiling on super-hydrophobic surfaces. Aluminum, copper, titanium, stainless steel, which are textured by etching, hydrothermal etching, or laser texturing, followed by some sort of chemical vapor deposition. And maybe just a recent result from with the titanium. This is hydrothermally etched titanium covered with a sealant. It's a nice structure, and it is very effective for a boiling. You see the same image as I showed you before. So this is the reference surface with multiple repetitions, and this is micro nano structure hydrothermally etched titanium, and after hydrophobization you get another stage of let's say enhancement, and no vapor film is observed on those surfaces if the experiments are done correctly, basically. And yeah, this is everything. Matteo encouraged me to not to be too long. I tried that. I would like to thank my colleagues, especially Matevz, highlighted in red, who did a lot of measurements on thick samples, and from another laboratory, 𝗂𝗁𝗁𝗁𝗁𝗁𝗁𝗁, who is the brain behind laser texturing. And a lot of stuff discussed today will be published, I hope, in January in a book chapter, materials with extreme wetting properties. Thank you, guys.